Okay, this is problem number 11, and this is a couple of ones that I tried to share the entire screen and apparently it didn't work. So I'm going to go back. I've got them worked out already, but I've got to I just have to go and explain them again. And that little cursor, there we go. Cursor thing is not working right now, so there we go. And we're back in business. Okay, so problem number 11 is we're asked to find the critical numbers and areas of increasing and decreasing functions. So this is our function. It's a polynomial. It's a parabola pointing upward because it has a positive x squared. And the first thing to do is find the critical number. So we take the derivative of the function, which is that. Set the derivative equal to 0, or where the function derivative of the function does not exist. Well, this exists at all numbers, so we just have to find the values of x where that go to 0. So we set it equal to 0, and you can factor out a 2. And so if you solve that, when x equals 1, this goes to 0. So we have one critical number at x equals 1. So now we break up our interval. So we have interval, test value, sign, and conclusion. So the intervals are from negative infinity to the critical number. From the critical number to positive infinity. This covers every number except the critical number. Find a test point, which means a value of x, which is in this interval, and in that value of x, which lies in this interval. So in this case, 0 is the one we always like to choose. And over here, we'd pick x equals 2. Nice even numbers, or nice whole numbers. And then we evaluate the derivative at those values of x. So here's the value of the function. I called it f. I should have called it g. So you just plug 0 in here to get the derivative, and you get 2 times 0 minus 2, which is negative 2, which is negative, so we put a negative sign in there. And here we have put in 2. 2 times 2 is 4, minus 2 is positive 2, so we put a positive sign. So that's where those come from. And we make the conclusion based on the sign of these. So because it's negative, the function is decreasing, and because the derivative is positive, it's increasing. And that's all we had to do for that problem. Okay, we're doing 14. So 14 is not a polynomial. It's a actual rational function. I'm just going to leave it at this. Leave it as this. Anyway, what we're doing is going to find critical numbers first. So what's part A? We'll call critical numbers. I think I forgot listing in the last one. Critical numbers. So what you do there, you take the derivative. So what you get is 1. And the derivative of this is what? Well, it's x plus. So we're going to rewrite it before we take the derivative. So it's going to be negative from the negative 1. So I'll just put negative 1 in there. Negative 1 times 4, the constant, times x to the minus 2 power. So we get 1 plus 4 over x squared. And we set that equal to 0. And I'm just thinking ahead here. Oh, yeah. I realized I made a mistake because I wasn't going to get a solution, so let me get that correct. Okay, so negative 1. So we have pause. I thought about the negative 1. I did it twice. So anyway, it's going to be negative that. So we take that and we set it equal to 0. So what we do, I'll multiply everything by x squared. So we'll get x squared minus 4 is equal to 0. 1 times x squared is x squared. Negative 4 over x squared times x squared. The x squareds become 1. You get 4, and 0 times x squared is 0. Okay, so now we can factor that. So we'll have x plus 2 and x minus 2. So that means we have critical numbers at x equals negative 2 and x equals 2. That's where we've taken the derivative, set it equal to 0, solve for the values of x where the derivative is equal to 0. So those are our critical numbers. Okay, so step number 2 is to make up your table. I'll call step B is table. Okay, so we said just previously that it's always 4 rows and the number of columns. You've got your heading column, and then you have one more. For each critical number, you have a column plus you add 1 to that. So we've got 2 critical numbers plus 1 additional column. So the headings are the same as we had in the previous problem. You have interval, you have test value, you have sign of, in this case, y prime, because we're using y, so let's do that, and then you have a comment or something like that. Let's see, what do they call it? Conclusion. Okay, so here are our critical numbers. So we start off at the lowest thing in the domain, and you go to the most negative critical number, which is 2. Then we'll go from negative 2 to positive 2, so you go between the critical numbers. Kind of proceed from left to right, smaller negative to positive. And then we go from 2 to positive infinity. So those are our 3 intervals. Something may happen here. We don't know. Okay, that's critical numbers. Something could happen there, but we can have the case where nothing, it doesn't change from increasing to decreasing. It could just stay increasing. So don't assume you have something changing in terms of the direction of increase or decrease across critical numbers, but you have to include them all to start with, just to be on the safe side. Okay, what value? So I'm gonna say x equals negative 3, x equals 0, and x equals positive 3. So this negative 3 is in this interval, 0 is here, positive 3 is there. So the sign, so you go back to the derivative thing. So what we want to do is we want to find out what y prime is at x equals negative 3. So you get 1 minus 4 over negative 3 squared. So is that going to be positive or negative? Well, the question is this term here positive or greater than or less than 1? If it's less than 1, then it'll be positive, because you'll have 1 minus a number less than 1, which will be positive. So you get 4 ninths, not 4 over negative 9, because you square negative 3, you get positive 9. So 4 ninths, 1 minus 4 ninths is 5 ninths, which is positive. So that's good. Y prime at x equals 0, we'll get 1 minus 4 over 0 squared. Well, actually, so what do we get there? We get infinity. We have or does not exist. So so what did I do wrong here? Because originally I just got 2 critical numbers. And what happened is if you look at this point, you'll see when x equals 0 that the derivative goes to infinity. So we actually have to add an additional column. So let's do that. So let's I'm going to take this table. I'm going to make it one more column, because I really got 3 critical numbers: 2 where the derivative goes to 0, and 1 where the derivative does not exist. So those are all critical numbers. So 4 rows, 3 critical numbers. So I go 1, 2, 3, and then add 1 additional one. Okay, so that's my table. It's one extra column, so I have to make sure I don't draw too big here. Interval, test value, sign and conclusion. Okay, so we go from negative infinity to negative 2. We go from negative infinity to 0, from 0 to positive 2, and from positive 2 to positive infinity. So that's how it's broken up. So the test value, negative 3, negative 1, and I see I made a mistake here. I've got to write this down correctly. So it's negative 2. So we go from negative infinity to negative 2, negative 2 to 0, 0 to 2, 2 to positive infinity. We've got the whole domain covered. So those are my test values. So I have to go back and fix this thing here, because what I found out was that my function did not exist there, so that wasn't good. Okay, so now we do y prime of x at x equals negative 1. So we'll get 1 minus 4 over negative 1 squared. So that's 1 minus 4. So it's negative 3. So the important thing is it's negative. So we found this was positive, this was negative. Okay, let's see what y prime at x equals 1 is. We get 1 minus 4 over 1 squared, which is still negative 3, so it's negative. So we put a negative sign there, and the final one is y prime at x equals 3. So you get 1 minus 4 over positive 3 squared. Well, negative 3 squared is the same as positive 3 squared, so this conclusion is the same. It's positive. It's positive. So what we can say is we're increasing here, we're decreasing here, we're decreasing here. Again, I'm looking at the sign of the first derivative, and then we're increasing. Okay, so I'm going to add a page, and I'm going to plot it, and then we'll bring it over so we can see both of them at the same time. So the function was x plus x divided by 4. So let's graph that. And so what's going on here? I think I did something wrong. Oh, x, 4 over x. It's like, what? 4 over x. Okay. So if I do that, there we go. Okay, so let's take a picture. So there we go. So what we did was we found that there were critical numbers at x equals 1 or negative 2, which is right here, and at positive 2 and at 0. So we broke the interval up. So this interval, negative infinity to negative 2, so that's the first interval. The second interval was from negative 2 to 0. That's this interval. And we went from 0 to 2, which is this interval. And then we went from 2 to positive infinity. So those are the 4 intervals. This one, this one, this one. We didn't include negative 2, 0, or 2 in the intervals. So then we took our test values. So we picked a test value of 3. So there's test value there. And we came up with some number, and it was negative. Actually, that's not the test. Test value is applied to the derivative, not to the. So we don't. That's not something we want to do. So anyway, we didn't do the value of the function at x equals negative 3. We found out what the derivative, and you can see it has a negative slope. So it's positive slope. So it's increasing. We evaluated the slope at x equals negative 1, which has a negative slope. We went to x equals positive 1, We found that has a negative slope. And we go to x equals 3, which is right here, and you can see that has a positive slope. So what we can see by these green lines, positive slope, increasing until we get to here. Then we decrease until we get, it says decreasing until we get to 0, and then it changes over, but it's also still negative slope. So this is decreasing. And then after x equals positive 2, it changes, and we have a positive slope, so it's increasing. So we go increasing left to right, from left to right we're getting bigger, more positive. At x equals negative 2, we change from increasing to decreasing. We continue to decrease. We jump over 0, which is a vertical asymptote, and we're still decreasing. We go from negative infinity to positive infinity. So when we go from positive infinity down here, we're decreasing, decreasing, until we get to the critical number, x equals 2, and then we change from decreasing to increasing. This is problem number 18. Again, we're supposed to be looking for the critical numbers. We again have a polynomial, and so to find the critical numbers, we take the derivative of the function, which is 2x plus 8. So that equal to 0. 2x plus 8 equals 0. Solve for x where that's true. So you can divide by 2, and then move the 4 to the right-hand side. And so, well, you factor out of 2. This has to be 0 for this to be 0, because 2 is always 2. It's always positive, and it's always 2. So this term has to go to 0. So we set that equal to 0. Subtract 4 from both sides, and we get x equals 4 as a critical number. So we have one critical number. Next thing we do is make our table. Again, we have just 2 intervals because we have one critical number, so we have 2 intervals. So our interval is from negative infinity to negative 4, and from negative 4 to positive infinity. We pick test values within those intervals. So negative 5 is the next whole number that's less than negative 4, and we put 0 in here. We don't use negative 3 just because it's easier to evaluate the interval or the derivative. So now we calculate the sign of the derivative. So let's go down here. So we plug in negative 5 into the expression for the derivative, and you get negative 2, so it's negative. And then we plug in 0 for x in the derivative function, and we get positive 8, which is positive. So we know it's decreasing in this interval, and we know it's increasing in this interval. And we only have to do one test value, because the only time a function changes from increasing to decreasing is at critical numbers. So we don't have any critical numbers except here, so we know it's going to be, if it's going to be decreasing in this whole interval, it's going to be increasing in that whole interval. And if we plot this function, you'll see that at x equals negative 4 is where we have 0 slope. It's where we have a minimum. Less than negative 4, which is this interval, is decreasing. At x greater than negative 4, the function is increasing. It has a negative slope here, positive slope there. Okay, we're on problem 24, which I just worked and made an error, so I went back and corrected it. I found the error by plotting the result, and I realized my graph was not what I thought it was. So that's always the advantage of plotting these things. Find your errors. So anyway, the original function was this. And I went ahead and multiplied it out, so it would just be easier to take the derivative. So if you multiply this out, you get x squared plus 4. X plus 4, and this is where I made my mistake, is I had x minus 1 here, and then I changed it to x plus 1, and then I did it all wrong. So now when you multiply this out, you'll get x cubed plus 4x squared plus 4x from this part times x, and then you get negative x squared minus 4x minus 4, and the 4x, and you get negative 4x go away, and so you don't get that term. And then you have x cubed plus 4x squared minus x squared. 4 minus 1 is 3, You get that? Okay. So that was the function, just simplified. Before I took the derivative. To find the critical numbers, you take the derivative. So you get 3x squared plus 6x minus 0. Factor out 3x. That leaves you with x plus 2. So set that equal to 0. And so the two solutions are x equals 0 and x equals negative 2. So those are my two critical numbers. And this is, again, my first derivative. So because we have two critical numbers, we make our table as 4 rows, and we have one column for the headings. We have two critical numbers, so that's 3, plus one more is 4. So we make it 4 columns. And then we break the interval up. Go from the entire domain. We go from negative infinity to negative 2, which is our first critical number, from negative 2 to 0, which is our second critical number, from 0 to positive infinity. So those are the three intervals. Then we pick test values in those intervals. So negative 3 is in this interval, negative 1 is in this interval, and positive 1 is in that interval. And then you evaluate the function, or the derivative, at these values of x. So at x equals negative 3, you plug it in there, and you get positive 9, which is positive. So you put a positive here. You plug x equals negative 1 into the expression for the derivative, this equation here, and you get negative 3. So you get a negative sign. And if you plug in x equals positive 1, you get 3 times 1 squared plus 6 times 1, which is positive 9. So that's positive. So with those signs, you can then make the conclusions that the function is increasing here, decreasing there, increasing there. So to look at the maximum, relative maximum minimums, you look from changing from increasing to decreasing, or from decreasing to increasing. So we see that across the critical number at x equals negative 2, it goes from increasing to decreasing. That's a maximum. And at x equals 0, our second critical number, it goes from decreasing to increasing, which is a valley, which is a minimum. So those are our results. And then if we plot the function correctly, I plotted it correctly last time, it's just I transcribed it wrong. So we have x plus 2 quantity squared times x minus 1. So there's your function. And let's just add that to the graph, to page. So there you go. And I think I put it on the wrong page. So, well, it's probably okay where it is because I can see my table. So here are critical numbers. X equals negative 2, x equals 0. So we break it up into three intervals, from negative infinity to negative 2, which is here. We go from negative 2 to 0, which is this interval. And then we go from 0 to positive infinity. So we have three intervals. We evaluate the derivative at negative 3. So that would be 1, 2, 3. So it's positive. We evaluate the derivative at negative 1, x equals negative 1, which is it's decreasing, and then we evaluate the derivative at x equals 1, which is positive. So we go increasing, decreasing, increasing. Where it goes from increasing to decreasing, we have a local maximum, and where we go from decreasing to increasing, right here, we have a local minimum. So that's it. Okay, this is problem 30. And let me just cover up a few things here so we can get ahead of ourselves. So this is our function. What we're doing is looking to find the critical numbers. So we take the derivative. We have 1/3 times x minus 1 to the minus 2/3 times the derivative of what's in the parentheses, which is just the derivative of x is 1, the derivative of 1 is 0, so we just get 1. So we're using the chain rule. And then I move this to the denominator, make this positive. Okay, so the numerator never goes to 0, so we don't have any zeros. We don't have any critical numbers as far as 0 slope. But you can see that this is going to go to 0 when x equals 1. If we divide by 0, then we have an undefined slope. So we have a critical number by the other way of having critical numbers. So we have one critical number, so we'll break it up into two intervals. From negative infinity to 1, our critical number, and from 1 to positive infinity. Now we pick test values. So I'm going to pick 0 here because that's always the one to choose if I can choose it. And here I'm going to pick 2, which is the smallest whole number greater than 1. So those are my test points. And then I'm going to plug those into here. See what I get. So f prime of 0, you put 0 in, you'll get negative 1 to the 2/3, which is positive 1. So this becomes positive 1. Why is that? Well, neither way you do it. If you square negative 1, you'll get positive 1. Take the cube root of positive 1, you get positive 1. Or if you take the cube root of negative 1, you get negative 1. And you square negative 1, you get positive 1. So either way, you get positive 1 out of this thing. So you're going to have a positive slope. So you put positive. Okay. Now if you do the second one, 2, you get 1 over 3 times 2 minus 1. Well, 2 minus 1 is 1. So 1 to any power is 1. So you still get positive numbers. So in this case, we don't have a change. We have both positive numbers here. So it's increasing up to this critical number, and then it's increasing again. So what does that mean? Well, here's the function. Here's the plot of the function. It's positive, increasing, 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 goes to infinity slope, then it's increasing, and it increases less as we go along. So we broke it into two intervals, from negative infinity to positive 1, and from positive 1 to positive infinity. So we do have a something weird going on there, but instead of being a 0 slope, in this case it's an infinite slope. Okay, 35. Here's our function, which is a it's a rational function, and we're going to have vertical asymptotes at -3 and +3 if you factor the denominator, and you'll have a 0. It'll equal 0 at 0, x equals 0, because the numerator goes to 0 at that point. Now what this is showing was if this was x squared plus x squared minus 3 quantity squared, then you would have a double thing where it both goes to infinity. But in this case, one's going to go to negative infinity, and the other side's going to go to positive infinity. So here's our quotient. We have our two terms, the numerator and the denominator. We take the derivatives, get 2x and 2x. So now we take these two together, multiplied by these two multiplied together, minus these two multiplied together, divided by this term squared. So that's using the quotient rule. And if we multiply the numerator, you'll see we have 2x times x squared, and we have negative 2x times x squared. So those drop out, and all we have is negative 18x. And then the denominator is x squared minus 9 quantity squared, because we just started with it by itself here. So that's the quotient rule. So now we want to find out where the derivative is equal to 0 or is undefined. So how do we do that? Well, we set the numerator equal to 0, and the denominator can be factored. So x squared minus 9 is x plus 3 times x minus 3. So this will go to 0. The denominator will go to 0 when x equals -3 and when x equals positive 3. So we have three critical numbers. We have one where the numerator is 0. The numerator is 0 when x equals 0. And then we have that the function does not, the derivative does not exist at either x equals -3 or x equals positive 3. So we have three critical numbers. So we'll need 4 columns in our table. Actually, we'll need 5 columns. 4 columns for the intervals and 1 column for the labels. So our intervals go from negative infinity to -3. -3 to 0, 0 to 3, and 3 to infinity. So these critical numbers are associated with the function not defined, and this is where the function, the derivative, pardon me, this is where the derivative is not defined, and this is where the function is equal to, derivative is equal to 0. Okay, pick test points, -4, 1, +1, I mean -1, +1, +4. I can't use 0 because that's one of the critical numbers. So then you're going to plug that into this expression, the derivative. And we're just going to do a ballpark look at what's happening. So you've got -18 times -4. That's going to give you a positive number here. So that's positive. Now the denominator is squared, something squared. So anything squared is positive. So no matter what the value of x is, this is going to be positive. So if we can find the sign of the numerator, then we'll have the sign of the function. So when x is negative, the numerator is positive because you'll have negative times negative. So that's positive, that's positive. Likewise, when the x is greater than 0, this numerator is negative. And therefore you have negative values for the values of the derivative at the test points. Then you make your conclusions: positive, positive, negative, negative, increasing, decreasing, decreasing. So that's how you get the increasing, decreasing stuff. So we're not going to have a maximum here, or we're not going to have a maximum there. We can either have a minimum or maximum at that point. So our local extrema, there's one extrema where we go from increasing to decreasing, and increasing to decreasing is a little mountain, so it's a local maximum at x equals 0. Here we have vertical asymptotes, so nothing happens. We don't have extrema, we just have function not existing. And finally our graph. So let's put it on one page. So what we did is we saw that the derivative did not exist at x equals -3 and x equals +3. That's because the derivative does not exist. It goes to negative infinity and positive infinity. Well, actually it goes to positive infinity on both sides, but it does not exist. We have a critical number at x equals 0 because the derivative is equal to 0. We have a 0 slope of the tangent line. Here we were increasing before the critical number and we were increasing after the critical number. For the second critical number, x equals 0, we go from increasing to decreasing, which means the local maximum. And then at x equals 3, we're a negative slope because we're getting more negative, and the same thing true here, still negative. So we don't change the direction across that particular situation. Okay, we're on problem 42. And as you can see, this is another one of these that I recorded and then it didn't show up. So anyway, it's one of the trig function problems again. So original function is that. We take the derivative of this function. It gives you 1 plus 2 cosine of x. Set that equal to 0. And we get the cosine of x is -1/2. So now the question is, what values of x give us, when you take the cosine of that, you get -1/2. So we're going to find a reference angle, then determine which quadrants it's in based upon the sign of this original question. So you take the reference angle by taking the inverse cosine, because that's cosine of the absolute value of 1/2. So it's the inverse cosine of 1/2. We get 1.047 radians. Multiply and divide by pi. 1.047 divided by pi, multiplied by pi. So now we're going to have this number times pi as the result. So you'll get 0.333. 1.047 divided by 3.14156 is 0.33. So that's 1/3. Therefore, the answer is pi/3. That's in the first quadrant. Now, in what quadrants is the cosine negative. So again, we can use the unit circle. The sign is positive in these two quadrants and negative in these two quadrants, whereas the cosine is positive in these two and negative in those two. Or we can use all students take calculus. So in what quadrants is the cosine positive? It's positive in the first quadrant and fourth quadrant. Therefore, it's negative in the other two, which is 2 and 3. So our solutions are going to be in the second and third quadrants, Q2 and Q3. So for the second quadrant, we say that the angle, the solution, is pi minus the reference angle. Pi minus pi over 3. We have 1 minus a third is 2/3, so we get 2/3 pi as our second quadrant solution. Our third quadrant solution is pi plus the reference angle. Pi plus pi over 3 is 4 pi over 3. And you can always check it by just plugging these back in. So if you take the cosine of 2 pi over 3, you'll get negative 1/2. And if you do the cosine of 4 pi over 3, you'll get negative 1/2. And you'll say, I did it right. If you don't, if you plug it in, if you plug your solutions in, they don't give you this answer, then you've done something wrong. So our two critical numbers are x equals 2 pi over 3 and x equals 4 pi over 3. Now we have two critical numbers, so we're going to have 3 intervals. So our intervals are from 0 to our first critical number, from our first critical number to our second critical number, and from our second critical number to our upper bound, which is 2 pi. Pick some values of x. This is probably the hardest part for you guys because you're just not used to dealing with angles that are in terms of radians. So 2/3, 1/2 is less than 2/3, so x equals pi over 2 is a good choice here. 2/3 and 4/3, well, 3/3 is in between, which is 1, so x equals pi is a good choice. And this one, 4/3 is less than 3/2, and 4/3 is 1.33, 3/2 is 1.5, 2 is 2, so this one is in the middle. So now we just plug those in. So we plug in pi over 2, this value, 1 plus 2 times the cosine of pi over 2. Cosine of pi over 2 is 0, so you just get 1. That's positive, so you put positive in your table. The second one is pi, so you get 1 plus 2 times the cosine of pi. Cosine of pi is negative 1. So you get 1 plus 2 times negative 1, which is negative 2. 1 minus 2 is negative 1, which is negative. You put that into your table. And the final case is pi theta equals, or x equals 3 pi over 2. So you plug that into your equation for the derivative. So we get 1 plus 2 cosine of 3 pi over 2. That's also 0. So you get 2 times 0 is 0. 1 plus 0 is 1. It's positive, so you put positive in there. Then you make your conclusions. Positive, increasing, negative, decreasing, positive, increasing. So that gives you what direction the function is going in. The critical numbers could be minimums or maximums if you have a change in direction. So we go from increasing to decreasing, therefore we have a change. We go from decreasing to increasing, which is another change. Now which one is the maximum or minimum? Well, at this critical number, 2 pi over 3, it goes from increasing to decreasing, therefore it's a maximum. At x equals 4 pi over 3, it's decreasing just before, increasing just after, so it goes through a minimum. And then we can look at all this on the graph. So this is our function. Here it is between 0 and 2 pi. We have critical numbers at 2 pi over 3 and 4 pi over 3. So we have 3 intervals, from 0 to 2 pi over 3, from 2 pi over 3 to 4 pi over 3, 4 pi over 3 to 2 pi. at those points we have zero slope. In the interval, this interval, it's increasing. After 2 pi over 3 it decreases until 4 pi over 3 where it changes. We go from increasing to decreasing. It gives us a local maximum. Here we go from decreasing to increasing. That gives us a local minimum. Notice my test points. I wrote those down. This is pi over 2, so we got a positive slope. Pi, which is here, gives us a negative slope. 3 pi over 2 is here, it gives us a positive slope. Okay, this is the last group of problems from section 3. And what they're asking for is, so the graph of f is shown in the figure. Sketch the graph of the derivative. So I've actually done something like this before, I think, but we're going to do it again. So this one, the derivative is the slope of the line. So you can see the slope is constant and it's 0. So the curve of the derivative in this case is just 0 the whole time. Okay, here we have a straight line, so the slope is also constant, but it is not 0. So what is the slope? Well, we go rise, which is 2, run is 1, so we have a slope of 2. Therefore, the derivative is just going to be a straight line with a value of 2. Okay. Now here we have a slope of 0, so the slope is going to go through that point. So the function is -4, but the slope of the curve is 0. And you can see that it's going to be negative here because the function is decreasing, and it's positive. It looks like a tangent. I mean, it looks like a parabola. So it's going to look something like that. And if you think also if this is the equation of a parabola, the derivative of a parabola is a linear function. And so that's what that is. Okay. Now here we have a 0 slope. 2 places we have a 0 slope here. We have a 0 slope there. Because if you go straight down, you'll see that 0 slope, 0 slope. Now, the slope is positive and then negative. So what we're going to have is positive, so this is going to be negative, so it's going to be less than 0. And we also have a 0 slope right there too. So we have 3 places. We have 0 slope. So the slope is negative, so we're going to come from this direction. So the slope is negative, 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 then turns positive. And at this point it goes back through 0, so we'll go back down through 0. So the slope is 0. And then it's negative again. The slope here is negative, so the value is negative. And then we go through 0 again here, and then the slope is positive. So this has a characteristic of something like, y is equal to x cubed, plus blah, 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 some extra terms. So it's third order. This is a fourth order function because it's even, goes to positive infinity. It has 3 intercepts, but it could have 4 if this thing went up a little bit higher. Anyway, so it's the third order polynomial. Function is decreasing, increasing, decreasing, increasing. Less than 0, positive, less than 0, positive, so you can see the value. Okay, now here, the slope looks like it goes to infinity. Because it gets steeper, steeper, steeper. And here it's positive for the entire time. So let's just draw a line, vertical asymptote, right here. Now the vertical asymptote is not for the function itself, but it is for the derivative. And then this is going to go to 0 as time goes on. As you go out, it's going to get lower and lower and lower. So the slope approaches 0, therefore the function of the derivative. So I'm going to say it looks something like this. It's not really reciprocal, exactly reciprocal relationship. This is actually the function. If we looked at the function, it would be y equals square root of, let's see, it would be x plus 4. Why do I say that? Well, because when x is negative 4, y is 0, the function doesn't exist. If you go at less than negative 4, if you put negative 5 in there, you get negative 5 plus 4, which is negative 1. Square root of negative 1 does not exist. So we know the function doesn't exist over here. It just looks like a square root function. So if we were to take the derivative of that, y prime would be equal to 1/2. The derivative of this would be 1. And then we would raise this. This is the same as x plus 4 to the 1/2 power. So when you take the derivative, you get 1/2 x plus 4 to the minus 1/2 power. So you get y is equal to 1 over 2 square root of x plus 4. So it is kind of a reciprocal relationship. It's not 1 over x, but it's 1 over, it's basically the same shape as 1 over the square root of x. Okay, and then this one, we actually saw that in a problem. What's happening here is that the slope is positive, and then it goes to infinity right here, and then it still is infinity on this side. I mean, it goes to infinity, and then it goes back to 0. So let's see, it's going to be positive. So the derivative is going to take some form like this. So the slope is positive. As you get closer to 0, the slope gets more positive. And then afterwards, it still is positive, and then it comes down and looks something like that. I'm trying to remember if this was y equals like the cube root of x, maybe. Or is it x to the 2/3? I don't remember exactly. Anyway, which ended with this 1 over something. So it's kind of a reciprocal relationship, but I think it's squared. So it's probably to the 2/3. So if you had, maybe not. Anyway, I'm not asking you for the function, but again, you can see this is going to be symmetric, because it looks like a symmetric thing if I were to bend that over and switch it back over here. And anyway, the slope goes to 0 as you go to negative x, infinity. So the derivative is greater, it's positive, approaches 0, then as it gets near 0, as the function gets near x equals 0, the slope goes to infinity. After 0, it comes from positive infinity, and then gets a smaller and smaller positive value. So that's what this looks like.